We'll start the class. Let others join by. So is the PPT visible? Anybody will respond?
Yes, sir.
Okay, so we have been discussing this one, functions in Amazon Cloud. So next one is YouTube. So you all know that so it is the largest video sharing site. So which began in April 2006, and it is acquired by Google in November 2006. So this also is based on the content distribution networks. So it is going to stream so videos in terms of chunks. The same concept. So the CDN also is included in the test syllabus. So it uses HTTP streaming and it does not use Dash, so which we have described so previous class. So Google does not employ third-party CDNs, but uses its own private CDNs for distribution. So YouTube videos. So also third one is also there, so called as Kankan. It is also leading so peer-to-peer based video on demand provider. So but so it is in China. Okay. And it also uses the concept of BitTorrent that I described in the very first module. So which is based on the UDP. So those are the three things which you have in this one. Okay. So next one is the voice over IP, VoIP. So this is also important concept. Voice over IP end-to-end delay requirement is that so it is needed to maintain conversational aspect where a higher delay will be noticeable. So if it is less than 150 milliseconds, it is good, and greater than 400 milliseconds, you classify it as bad. So also there are issues such as session initialization and so value-added services, which wherein you want to where the callee will advertise IP address like support numbers and encoding algorithms, and value-added services like call forwarding, screening, and recording purposes. So coming to characteristics, yeah, the speaker's audio and so alternating talk spurts, silent periods. So where 64 kbps during talk spurts and packets generated only during spark talk spurts, and so 20 milliseconds so chunks you have. So at specifically so 8 kb bytes per second, and so that is specifically 160 bytes of data. Okay. So here the application layer header will be added to each chunk, right? So here specifically, so therefore the chunk plus header will be encapsulated into the UDP or the TCP segment. So the application sends segment into socket every 23 milliseconds. So actually this talkspurt, the concept of talkspurt comes in digital telephony. So it is a continuous segment of speech between silent intervals where only background noise can be heard. So that you call it as a talkspurt. So you're able to hear only the background noise. So coming to packet loss and delay. So packet loss will happen like IP datagrams will be lost due to network congestion. Like so router buffer overflow will be there. So the like we have described. And also there will be delay loss like IP datagram arrives too late for packet playout at the receiver. So because so in the concept of so while so video will be played will be sent from the server to the client. So you have seen the playout, right? So there could be also delays like so processing, queuing the network end system. So all could be so resulting in delays, right? And so you also could be able to see tolerate so delay up to a maximum of 400 so milliseconds. And also so loss tolerance is also so dependable on voice encoding like loss concealment. So packet loss rate between 1% and 10% can be tolerated. Okay, so this is the same thing that we have so gone through initially. Like so initially you may have a so constant bit rate transmission. So then in the previous class we have been discussing this. So then there'll be a variable network delay. You address it as a jitter, and at the client reception the video will be received, and at the client so video will be played out at the constant bit rate. So at the client. Okay, so at the client at a particular after a particular delay, the playout of the video will happen. Okay, so here end-to-end delays of 2 consecutive packets, that is, you can define it as a difference can be more than or less than 20 milliseconds. So that may happen due to the transmission time difference. So next is fixed playout delay. So we have seen variable playout delay that could happen. So receiver attempts to play out each chunk exactly q milliseconds after the chunk was generated, and the chunk has a timestamp t, and the playout chunk or the playout chunk at t plus q, okay, which we call. And the chunk arrives after t plus q, so the data arrives too late for the playout, and so data will be lost here. So those are the issues. And trade-off is that in choosing specific queue. So how do you choose queue here? Okay, so if you choose large queue, there will be less packet loss, and small queue will be better for interactive experience. So that is the uh, criteria for choosing the value of queue. Okay, and in the fixed playout delay, also you see that sender will be generating packets every 20 milliseconds during the talk spurt, and the first packet will be received at particular time r, and also first playout schedule will begin at particular t. Okay, if you see the diagram here, so you may see that first packet may get received at the particular time r. Okay, here. Okay, and so if the packets are generated and you receive the first packet at r, and you try to play the packet at or packet playout begins at t, and the second playout schedule begins at p dash. Okay, so therefore you are able to see that playout schedule is given by p minus r, and playout schedule is here at this particular point is p dash minus r. Okay, so that is how you will be able to calculate the values. So for adaptive playout delay, you calculate it as I, or you say I. So the goal is low playout delay to achieve it, and low loss rate. Okay, and the approach is to have the adaptive playout delay adjustment. So estimate network delay, adjust playout delay at beginning of each talk spurt, and there are silent periods compressed and elongated, and chunks still played out at 20 milliseconds during the talk spurt. So try to evaluate the exponential weighted moving average called as the EWMA. So it is very similar to the TCP round trip time. Okay, so which we have gone through there, right? So which we have already evaluated. So that is very similar to evaluating the round trip time. So the time it takes for the particular packet to move to the destination and also to come back. Okay, read the particular source. So that is what the round trip time which we have defined. So DI, that is a delay estimate after ith packet. So which you specifically address it as DI. Okay. So that is 1 minus alpha into DI minus 1, where alpha being very small constant, like you fix a value for alpha as 0.1. Okay. So plus alpha into Ri minus Ti. So Ri is the time received, which you call Ri, and so Ti is the time sent, that is the timestamp. So this Ra minus, so alpha into Ra minus Ti, so is the measured delay of the ith packet. Okay, so that is how you address it. Okay, so therefore you have the equation DI, delay estimate after ith packet. So it is 1 minus alpha into Di minus 1 plus alpha into Ra minus Ti. Okay. So also it is useful to estimate average deviation of the delay. So you try to evaluate the deviation now. So deviation is evaluated by the equation Vi. So Vi is equal to 1 minus beta into Vi minus 1 plus beta. So take the absolute of Ri minus Ti minus Di. So estimates DI, Vi are calculated for every received packet, but used only at the start of the talk spurts. Okay. So for the first packet in talk spurt, so playout time is playout time of particular packet I is equal to Ti plus Di plus K into Vi. Okay. So that is the given equation. So remaining packets in talk spurt are played out periodically. So this will be in the adaptive playout delay. So then how to recover from packet loss? So that is also an important criteria. So how to recover from packet loss? The challenge is that you have to recover from packet loss. So given small tolerable delay between original transmission and playout. Okay. And so each acknowledgement or negative acknowledgement takes one RTT. That is the assumption. So alternatively, the forward error correction. So FEC bit. So we have seen this usage here. So it is send enough bits to allow recovery without transmission. So in the simple FEC, so for every group of n chunks, so create redundant chunk by XORing so n original chunks. Okay, so that is how you evaluate it, right? So send n plus 1 chunks, increasing bandwidth by a factor of 1 by n, and you can reconstruct original n chunks if at most one last chunk from n plus 1 chunks with so playout delay. Okay, so that is the concept there. So if you just go through the diagram here, so you see that here, so there are four so packets like so 1, 2, 3, 4, and so you are going to make it redundant. So like so first packet is copied and so here so 1 plus 2, so two packets are there, so 1 and 2. Then so second packet is redundant, so 2 plus 3, second and third, and also so in the last so you have third and fourth. So suppose second and third packet get lost, so you see that so at the last, so you can reconstruct, or in the reconstruct stream, you see all the four packets are so reconstruct, even though there is a packet loss. Okay, so that is how you can recover from packet loss. Okay, so that is how it is, right? So because so from the original stream you are making it redundant, right? So the first packet is redundant now in the second, and second packet is also redundant, so third is also redundant. So even though there is loss of second and third, you are able to so reconstruct because of the redundancy that you are doing. So likewise here also, so recovery from the packet loss. So if you see that so all the packets are jumbled in the interleaved stream, and even though the packet loss happens, so in the reconstruct stream, so you see that so the audio chunks will be divided into smaller units, like 4-5 milliseconds units per 20 millisecond audio, and packet contains small units from different chunks. Okay, so this is interleaving specifically to conceal the loss, right? Or to suffer less loss from the packet loss. So if packet is lost, still have most of the original chunk. Okay, so that is also in this case you observe that there is no redundancy override, and but increases layout delay. Okay. So next you have the voice over IP, the Skype. So which you have the proprietary so protocol Skype. So it is a proprietary application. It is layer protocol, and so it has the message in of encrypted form. So here you have the peer-to-peer components. You have the Skype clients, so called as SC. Then you have so peer-to-peer components, the clients, right? So all these are clients. The Skype peers connect directly to each other for the voice VoIP call, and also you have the super nodes, right? The Skype peers with special functions. Okay. So you see that there is an overlay network among so SNs to locate SCs, the super nodes to locate the clients. Okay, so that is how the network is built, and also so you have the Skype login server, so which is placed here. So in this you have the Skype client operation. So it joins this client. The client joins the Skype network by contacting the SN, uh, and you also have the IP address cached, so using the TCP. So when it logs in using the username, password to centralized Skype login server, so as specified. So you just observe the diagram here. So it is shown in terms of steps. So next, so it obtains IP address from the callee from SN, the SN overlay, or so client buddy list, which we call. Okay. So then finally, the client so initiates call directly to the callee. Okay. So thereby, so two are able to communicate and initiate so the voice over IP call. Okay, and so in the concept, so you are seeing that so the peers are acting as relays. The problem is that so both Alice and Bob are behind the NAT. So network address translation concept, so which I have gone through. So if both are behind the network, so the NAT prevents outside peer from initiating connection to inside peers. So because NAT does not allow to make calls directly, and inside peer can initiate connection to outside. That is possible, right? So therefore, the relay solution is that Alice Bob maintain open connection to their SNs. Okay, like so Alice signals her SN to connect to Bob, and so Alice SN connects to Bob's SN. Okay, and Bob's SN, so connect to Bob's over open connection. Bob initially initiated to his SN. So that is how. So even though the NAT is there, so both Alice and Bob can initiate a connection, and they can initiate an voice over IP connection. Okay. So those are the concepts in so voice over IP. So which you have. So mainly there. So you have the concept of how to how to overcome the packet loss or conceal the packet loss. So the last concept is the two protocols, RTP and SIP, for the real-time transmission of packets. So first one is real-time protocol. So RTP specifies packet structure for so packets carrying audio, video data. The RTP packet also provides payload type identification, so packet sequence numbering and time stamping. And RTP runs in end systems. So RTP packets will be encapsulated in UDP segments, and it provides interoperability. Like if two voice applications, VoIP applications run RTP, they may be able to work together. And RTP, as specified, it runs on top of UDP. So there are RTP library or libraries which provide so transport layer interface, and so that extends the UDP. So in terms of providing port numbers and IP address, and also so payload type identification, and so packet sequence numbering. We said so packets will be numbered sequentially so as to identify each packet uniquely, and also so time stamping. Okay. So you see here, so you have the physical layer, data link layer, the IP, and RTP is placed on UDP. So because we have said, so RTP runs on top of UDP. So on the top of UDP, RTP is placed in the transport layer. At last, you have the application. So one of the example is taken here, like so sending 64 kbps, so PCM, pulse code modulation, encoded so voice over RTP. The application so collects encoded data in chunks, like so every 20 milliseconds is equal to 160 bytes in a chunk, and the audio chunk plus RTP header form RTP packet. So now RTP packet is what? So it is a audio chunk plus RTP header, so which will be encapsulated in the UDP segment. So this whole UDP segment, so we'll be having the audio chunk plus RTP header. So that is treated as a UDP segment. So RTP header indicates type of audio encoding in each packet, and the sender can change encoding during conference. And RTP header also contains sequence number and timestamp. So RTP and quality of service. So how do you address the quality of service? Associate quality of service with respect to RTP is RTP does not provide any mechanism to ensure timely data delivery or other QoS guarantees. Like in the UDP, because basically UDP we have said it is in best effort service. Okay, so it just makes best effort to deliver your packets, and there is no guarantee that your packets will reach the destination. Okay, so RTP encapsulation only seen at end systems, so not by the intermediate routers. That is one more point there. So routers provide best effort service, making no special effort to ensure that RTP packets arrive at destination in a timely manner. So that itself is the behavior of the UDP. So you have the RTP header. So you have the payload type, sequence number, timestamp, synchronization source ID, and miscellaneous fields. So these are the five so fields in the RTP header. So the payload type is of 7 bits, which indicates encoding currently being used, what type of encoding you are using. If sender changes encoding during call, sender informs receiver via payload type field. Okay. If he's going to change, he should intimate the receiver. So if the payload type is 0, so it is the pulse code modulation, so with 64 kbps. If payload type is 3, so it is the GSM 13 kbps. If it is payload type is 7, so if it is LPC 2.4 kbps. If it is payload type is 26, it is the motion JPEG. Payload type is 31, H261. If payload type is 33, MPEG to video. Okay. So second field, sequence number. If it is 16 bits, so increment by 1 for each RTP packet sent. And because so you're going to continuously sequence each packet. So it is incrementing every time by 1. So detect packet loss, restore packet sequence. So if you detect any packet loss, you have to restore the packet sequence. So timestamp, so it is 32-bit long, 32 bits each. So sampling instant of first byte in RTP data packet. So it is for audio and timestamping clock increments for one of each sampling period. Like so 120 seconds, milliseconds for 8 kilohertz sampling clock. And also you see it generates so chunks of 160 encoded samples. And so timestamps increase by 160 for each RTP packet when source is active. Okay. And so the synchronization source ID field, so it is also 32 bits long. It identifies source of RTP stream, and each stream is RTP session has distinct the SSRC, the synchronization source ID. Okay, so last one is the messengers field. So the last protocol is SIP. It's also the last concept in this module. So session initiation protocol. So it has a long-term vision that all telephone calls, video calls, so take place over internet. And people identified by names or email addresses rather than by phone numbers. And they can also reach callee no matter where callee roams, no matter what IP callee is currently using. Okay. So look at the services offered by the SIP, that is session initiation protocol. So SIP provides mechanisms for call setup, for caller to let so callee know that whether she wants to establish a call. So caller and callee can agree on a media type, like so what type of encoding and so when to particularly end a call. And also to determine current so IP address of the callee, and also map so mnemonic identifier to current IP address. And with respect to call management, so you can add new media streams during call, change encoding during call, and invite others and transfer or hold calls. So just like your all the call facilities that you have in your mobile. Okay. So one of the example of setting up a call to known IP address is given here. So if you consider the example of Alice and Bob, so Alice SIP invite message indicates her port number. So just observe the very first initiation. So invite Bob at 193.64.210.89. So it is invite message indicates her port number, IP address, and encoding she prefers. And to receive the she prefers to receive GSM. So Bob is going to reply now with 200 message. So 200 means okay. So we have seen this. Okay. In HTTP, so most of the codes we have seen. So Bob's 200 OK message indicates his port number, IP address, and preferred encoding. So that is the pulse code modulation, right? And also specifying the port. So 5060, right? So then next. So after these exchanges, an acknowledgement will be sent. So with specifically replying port as 5060. Then SIP messages can be sent over TCP or UDP. So here it is sent over the RDT, RTP, UDP specifically. And default SIP port number is 5060, that is made use of. Okay. So this is the example, so which is specifically used to set up the call to known IP address. So please write down this example of setting up a call. So whenever SIP is asked. So also in this setting up a call, you have the codec negotiation. Like suppose Bob doesn't have a pulse code modulation, so MULA encoder. So Bob will instead reply with 606. So this code will tell not acceptable reply, and so listing is encoders. Then Alice can then send new invite message advertising different encoder. Right? So if specifically, so if Alice says some encoding, select some encoding, and Bob does not have. So Bob will send 606, that is not acceptable reply. Right? So listing his encoders. So like listing what all encoders he has. So then Alice can then will send a new invite message advertising different encoder. So also rejecting a call. So Bob can reject with replies like so busy, gone, payment required, and forbidden. Okay. And so media can be sent over RTP or some other protocol also. Right. So this is the sample of an SIP message. Right. So here you have an invite SIP at SIP. So the SIP protocol. So bob at domain.com, SIP 2.0 version. So via the SIP 2.0, which is mainly using UDP, then you name the IP address. So from SIP Alice, this is from alice.com to SIP to using the SIP protocol to Bob. So caller ID is specified and the content type, and so content length is also specified, right? So here we don't know Bob's IP address, like intermediate SIP servers will be needed. And Alice sends or receives SIP messages using SIP default port 506. Okay, so that is specified here by default. And Alice specifies in header that a SIP client receives SIP messages over UDP. Because as we have said, so underlying may be used UDP. Okay, so this is the SIP message. So also name translation and so user location can be specified, like the caller wants to call callee but only has callee's name or email address. And they also need to get IP address of the callee's current host. Okay, in which case, so user moves around or also so uses a DHCP protocol. So this we have seen dynamic host configuration protocol, and user has different so IP devices, like he may use a so PC or a smartphone or some associated as a card device. Okay, and so also the results obtained so can be based on the time of the day, and the caller so don't want some boss to call you at home, or the status of the callee like so call sent to voicemail when call is already talking to someone else. It's all these options so can be specified there. So associated, so also one more concept is there, like the SIP register. So this is also one important concept in SIP. So where one function of the SIP server is the registrar. So when Bob starts SIP client, so client sends a SIP register so message to Bob registrar server. Like so, this is the registrar message. So this is the registrar says it is a registrar SIP domain.com SIP 2.0 version. So from SIP from it is the Bob to Bob at domain, and it expects for the period of 3,600 seconds. Okay, and so one more function is of the proxy. Right, so this proxy concept, SIP proxy. So Alice sends invite message to her proxy containing address like so bob at domain.com, and the proxy will be responsible for routing a SIP message to the callee. So all of you please enter your so today's attendance in the chat box. So Bob sends a response back through same set of SIP proxies, and so proxy returns Bob's SIP response message to Alice. Okay, so which will contain Bob's IP address. And so SIP proxy will be analogous to local DNS server plus the TCP setup. Okay, so like you have the one of the example here. So this one, so just like so how to resolve the particular DNS. So this is the same thing. So it is mentioned stepwise. Right? So I'm just going to summarize this. So where so you have initially you have so all these like so this is the client 128.119.40.186. Then you have the UMAS SIP proxy, then poly SIP registrar, then this Uricom SIP registrar, and this is the another client. So in step one, Jim sends invite message to UMAS SIP proxy, then that gets forwarded to the poly registrar server. Then in third step, so the poly server will return direct response indicating that it should be it should try ktet so euro.com.fr. Okay, so that will be forwarded to UMAS proxy forwards this particular request to this Euro SIP registrar. Then, so that gets forwarded to registrar forwards invite to 197.87.54.21. So at last in step 6, so once again it replies back, and 6 to 8 the SIP response will be returned to Jim. Okay. At last, so data flows between these two clients. So this is going to so end so this particular module. So I think 3 more have not entered the attendance.